Quick review, the first line of defense is your skin, and that's a powerful barrier. Makes its own sort of toxic thing to germs called lysozyme. The openings are the weak spots, but they're guarded by cilia and mucus. Second line of non-specific defenses is the inflammatory response, which when you get invaded by bad guys, the non-specific way you fight them is by increasing blood flow to the area, which does several things. First of all, it allows good guys to get in there. The good guys that you see first are the phagocytes, the marines of the white blood cells. They come in, they gulp in as many bad guys as they can, and then they sort of self-destruct and kill all those bad guys. That's what you see as pus coming from an infected wound. That's dead phagocytes and dead bacteria and viruses. You also tend to heat the area up or to heat your whole body up, depending on what you need, which slows down bad guys and speeds up good guys, and doesn't make you feel very good. Then there's interferons, a specifically antiviral thing that both disrupt viruses and communicate with other cells that you're in trouble. Any questions about that stuff? Then we just touched on the very first step of specific immunity. The very first step for both kinds of specific immunity is called the macrophage, or sometimes it's called the antigen presenting cell. It's the thing that, like we said in my terrible analogy, basically swallows up bad guys, chops them up, and then wears them to show them to other good guy cells. Right? Everybody with me so far? Because from here it gets a little more complex. So the macrophage is always step one. It displays what we call the antigens. That's like marker proteins for bad guys. Antigens are the pathogens it swallows, and tells the T cells what those pathogens look like. There's a chemical called interleukin-1 that helps them activate those cells. You don't really have to worry about the interleukins. Next step is those T cells we mentioned. First of all, helper T cells. Helper T cells have two jobs. Number one, they show B cells which antibodies to make, and number two, they tell T cells, killer T cells, which cells to kill. There's another chemical that it uses to activate those next cells in the process. Again, you don't have to memorize the interleukin 1 and 2. There will not, well, there could be one extended response question, but not for that. It'll be mostly. Yeah. Okay. All right. Good? Yeah. I'll share the. Yeah. Just a second. I'm just taking it in. You good? Yeah. Quick side trip here as far as helper T cells go. You may or may not know that there is one kind of viruses that humans can get infected with. I told you viruses are pretty specific. There's one kind of virus that is specific to only helper T cells. Anybody know which one? That would be HIV. Virus that causes AIDS. Specific to human helper T cells. Which is sneaky, because that doesn't kill you, right? Destroying your helper T cells is not immediately lethal. The problem comes in that when you lose all your helper T cells for a while, you now have lost the ability to produce antibodies. And antibodies we'll talk about in a minute, but they're basically your ultimate weapon. And so when your T cells are down, your ultimate weapon is also down as far as new infections go. And so AIDS victims, typically what gets them is normally harmless diseases, diseases that you wouldn't even notice you had because your immune system's so good at fighting them off. Well, they don't have that because their B cells aren't being told by helper T cells what antibodies. Yeah.
What's the difference between AIDS and HIV?
HIV is the name of the virus, which is human immune deficiency virus. So HIV. AIDS is the syndrome. It's acquired immune deficiency syndrome. So it's basically the set of symptoms that happens when you're infected by HIV. It's the difference between SARS-CoV-2, which is the name of the virus the coronavirus that we're dealing with this year, and COVID-19, which is the disease itself. Does that make sense?
Yeah.
We're going to make a little shift here that I think will help you organize this information. I want you to basically take an arrow, maybe a different color if you have it, because it always starts with the macrophage and then goes to helper T cells. But then from there, there's two paths. So we're going to split a little bit. So in your notes, kind of make two columns with arrows going to each column. And one column is going to be this. In other words, you can take this and bunch it on the left side of your paper. So you get that this is one path we can take from helper T cells. This is called cell-mediated immunity. And what happens here is that some of the helper T cells turn into what we call killer T cells. These are literally killer cells. These are cells that are able to go poke holes in other cells and kill them. Yeah, we're there. We're at the killing part. Grant's been waiting. Really, they're only good at killing eukaryotic cells, so not much good against bacteria or viruses. But if you're invaded by a fungus or a protist like malaria, they're great for that. They're also great against viruses or cancer because they're good at killing your own cells. And sometimes that is necessary. If cells are being completely taken over by virus, in certain kinds of cancer, your body is able to differentiate and kill. That's a good thing, poking holes in your own infected cells. Basically, they poke holes chemically and cause those cells to rupture. The dark side of this is that when you have autoimmune problems, these cells are typically the problem. These cells are the ones that will go after healthy cells when you don't want them to. This is also the cells that are a problem when transplant rejection happens. Like, when the cornea transplant or the liver transplant or the skin graft is being rejected, it's because your immune system is sending in cytotoxic or killer T cells to poke holes in those cells and they die. But so this is one part, right? This is what we call the cell-mediated immune system. Then the other path, and here's where you get into the right-hand column, and just draw another arrow coming from helper T cells. And what's on the next slide will go in there. Does it make sense what I'm asking you to do? Okay, good. I've done it before, but I just thought of it. The other path they can take is called humoral immunity. And so instead of a cytotoxic killer T cell, we go to the B cell. B cells on your right-hand side, which we also call humoral immunity. These are kind of your ultimate weapon most of the time. They got to be, again, instructed by the helper T cells. They got to be shown what the bad guy looks like. But once they do, once they're shown, then the B cells start to inflate. They start to get bigger. They start to turn into what are called plasma cells. Plasma cells you can think of as antibody factors. Before you write that, though, let me show you what an antibody is, because most people don't really know that. Most people think of antibodies as more white blood cells to go kill stuff. They're not. They're much simpler than that. And what's key here is they're much cheaper to make. An activated plasma cell can dump millions of antibodies into your bloodstream. Antibodies are like proteins, but even simpler. This right here is an antibody. Antibody is basically two heavy chains, what we call two light chains of amino acids. So it's smaller than a protein, simpler than a protein. The key is that an antibody has two sites here and here that will stick to the antigens on the bad guys, right? They've been shown that the plasma cell was shown what the antigens look like, so it's now making antibodies where if there's a bad guy around, it's going to stick to that, which it wouldn't be a big deal because antibodies are actually much smaller than the bad guys. But then the other little fork here is going to stick to another bad guy. And then there's going to be more antibodies, and then one of them might stick here and then stick onto another bad guy. And you get the idea, it's kind of going to start clumping bad guys together. Bad guys can't do bad things when they're all stuck together, right? And antibodies have kind of a double function. Not only do they stick bad guys together, but they also function like flashing signs that say, kill me, kill me. And so your good guy cells come in and absolutely lay waste to these clumps of bad guys. So once you are dumping antibodies into your bloodstream, you're going to win. Okay? But the problem is it takes about a week for this system to fully crank up. But once they're there, once there's a bunch of those flowing through your bloodstream, bad guys are in trouble. You're going to win.
When you get your blood drawn, they take the antibodies out. That's like a process, or
When do they do that?
like with the coronavirus stuff, when it says like you take them.
So you don't specifically take them out. You separate the cells from the plasma, which is the liquid part, because the plasma has the antibodies in it. It's almost like you know how a centrifuge works? Spin, like if you take a tube of stuff and spin it real fast, the dense stuff will go to the bottom and the light stuff will be on top. That's basically how you separate cells from plasma. So I don't know about you, but for me, I hate being sick. And one way that I find helpful to look at being sick, usually you're sick for what, about a week? That's this week right here. Right? It's not that your body, it's not that the bad guys are winning. It turns out, you know, if something gets a good enough foothold in you, it takes about a week to produce your ultimate weapon. That week of you not feeling good is just ultimate weapon production time. I like to think of it that way, right? And when it's done, boom, bad guy's dead. Now, not only that, what's cool is your first infection by something, you make those antibodies, and it takes about a week, and your antibody levels get up to about here, right? And then the bad guys get killed, and your antibody levels go down. Except not all the way down. Antibody levels might go all the way down. But those T and B cells you made, you keep a few of them around. They're called memory T and B cells, and you keep those for about as long as you can. Maybe not your whole life, but an awful lot of it. You can put this back in the middle. Basically what this means is that the next time you're infected by this stupid pathogen, it's not going to take a week. Not only is it going to be way faster than a week, you're going to make like to where if your antibody levels came up to here on your first infection, they're going to come up to here much faster when you get reinfected. So it keeps that ability to fight off the pathogen and reduces the time and increases the strength of that secondary, we call it the secondary immune response. One of the worst diseases in history was smallpox. It's kind of like the worst of both worlds. It was as lethal as Ebola, but as contagious as Corona. Smallpox is airborne. And so lots of doctors were looking at, how we might protect people against it. And then this one doctor, Dr. Edward Jenner, noticed one group of people that weren't dying from smallpox. Anybody know? Anybody know this story? Which group of people didn't die from smallpox that he noticed? It was the milkmaids. It was the women, typically women, had the job of milking cows. All these women who milked cows weren't getting and weren't dying from smallpox. And so Dr. Edward Jenner kind of looked in closer, and he noticed that new milkmaids, as he kind of followed them around, new milkmaids would almost always develop this rash up their arms that they called cowpox. These milkmaids would all get cowpox. And if they had had cowpox, they would almost never get smallpox. And so Jenner did an experiment. He basically, and this was not an ethical experiment at all. The dude is kind of a little bit looked unfavorably on now because he did his experiment on kids. But what he did was when these milkmaids got blisters from cowpox, he would actually lance the blisters with a needle, get some of the fluid from the blisters, and then stick somebody else with that fluid to deliberately give them cowpox. You see where this is going? It turns out that cowpox has antigens, has those marker proteins that look enough like smallpox that the milkmaids and the people he's experimenting on have that primary immune response without getting very sick, without getting actual smallpox. It's like cowpox is smallpox light, right? So you get those memory B and T cells on the primary immune response, and then for the secondary one, boom, if actual smallpox comes, you're set. You got defenses, right? And so this was basically the first what? Jenner invented vaccines. Yeah, vaccines are basically an injection of a dead or weakened version of the pathogen you're trying to protect against. It essentially gives you that primary response and the memory B and T cells that come with it without giving you the full-fledged disease. When you get a virus, there's generally not all that much we can do. There's experimental therapies like the, convalescent plasma thing we saw in the Ebola movie. There's some antiviral drugs that can work pretty well. Tamiflu works pretty well against the flu at the right stage. So really the best defense we have And the only real kind of tried and true defense we have against viruses is before you get the virus, get the vaccine.
Exactly. That's what it leads to.
So it's not necessarily that you have it for long enough. Most kinds of flu, if someone dies from it, it's because their immune systems aren't strong enough. So like very old, very young people. Pandemic type flus, like the 1918 flu, has more to do with that it's new to your immune system. So your immune system overreacts, and that overreaction is actually what kills you. So kind of two different things there. But more detail than that, I can't really give you. Just want to, the thing I was doing with my hands with the immune response, let's just put that into a graph. This is what it looks like, right? You get infected. This is the week it takes for your humoral immune system, for the plasma cells to start cranking up antibodies, right? And so you get that level of antibodies, you fight off the disease, and then you get rid of the antibodies mostly, right? There's a few left. And then, second time you get infected, much steeper curve, that means it happens faster, and much higher peak of the curve. That means there's more antibodies, a stronger and faster response. And so this is what happens normally when you get something twice. This is also what we're taking advantage of when we give you a vaccine. We're giving you not quite, coronavirus. We're giving you not quite the flu. It's been messed with so that it's still got the antigens, but it doesn't have the ability to actually take over cells and give you the flu or COVID-19. And so you get this response without ever getting the full-fledged disease. Then if the real disease comes along, this is what happens and you don't even know it. Does that make sense? That's most of what you need to know about human immunity. We've got one technique to talk about tomorrow. It won't take long. I'm going to give you sample essays today. They are due Thursday. Right, so that's not tomorrow, but the next day. And we are going to downsize these essay questions a little bit. So listen carefully once everybody's got them. So there is one set of virus tricks that we have skipped for the sake of time in this unit. It has to do with the lytic and the lysogenic cycles. That would be number 2 and number 3. You can go ahead and cross out number 2 and number 3. You will not need to do those. You can also circle number 6, because that's the one thing we have left that we're going to clean up tomorrow. So don't try number 6 tonight. Don't do it until you've had a lecture tomorrow. So circle number 6. Everything else you should be able to get started on right now. You got solid 10 minutes to go. Is that the 35? Ooh, I shouldn't I? Help me remember tomorrow to do that. That's the blackboard period. Yeah, I'll check 35 guided reading tomorrow. That was due today, right? Good. I'll check it tomorrow.